Hey everybody, welcome to the second installment of our probability course, Sets and Counting. So we're especially going to be going over counting techniques. And please make sure that you have Probability Notebook 2 open in the Data Hub so you can follow along. This whole video is going to be pretty much doing examples, but as we go, we should think about, what types of counting is actually needed. So one quick question we're going to ask is, are there multiple draws? Are the draws made with or without replacement? Okay, because that's going to indicate whether we're using combinations and permutations or something else. Does the order of the draw matters? Again, that will differentiate between combinations where order doesn't matter and permutations where it does. Does the outcome change if the draw happens in a different sequence? Okay, so permutations are repeated draws without replacement where the order in which they're drawn does matter. Combinations are the same thing, but where order drawn does not matter. And again, this is review for a lot of you. Exponentials, repeated independent draws with replacement. So let's say you have a chance of rain. That's 20% for all 5 days this week in Dahlonega, Georgia. 20% chance of rain. What's, we would multiply those probabilities together. They're independent. Often in these situations, it's the same probability getting multiplied over and over. Like, I don't know, the number of heads. If I flip 10 coins or I flip 10 fair coins, how many of them come up heads? So we'll end up dealing with these with powers. That's what I mean by exponential, right? A power. Summations. Okay, so 10 people are in a room, and as they are greeting before the meeting gets started, every single one of the 10 people shakes hands with every single other person in the room. How many handshakes are possible? And this turns out that we need to sum up a certain group of numbers. And this applies to a few other situations, but the handshake problem is the quintessential idea here. And then permutations on a ring. So it turns out that if you line things up, say 5 people are standing in a straight line, there are 5 factorial or 5 permute 5 ways of ordering them. But when the 5 people are standing in a circle, there's 4 factorial ways of ordering them. Why? Because 5 of them are the same. They're just moving around like around the clock face, right? They're in the same order, but they move um, on that circle. So it's not n factorial, it's n minus 1 factorial. And we'll go over some of these ideas in more detail as we go on. Okay, so the examples are taken from the 50 counting questions PDF in D2L. There's also, it's also in our online course notes. We can find the same thing. So there are 16 students in math clubs, and in how many different ways could they select a president, vice president, and treasurer for a club? So these are draws without replacement. Why? Because once you've selected a president, that person cannot be either vice president or treasurer, right? So we're looking at 16 permute 3, right? 16 permute 3. Why? Because out of 16 possible officers, we're choosing 3, and order does matter. Okay. So reminding you of the formula and how it simplifies and the solution. 3,360. Okay. Number 3, the name of 11 students are placed in a hat. A teacher will reach into the hat and select 3 names, one at a time. Each of those 3 students receives the same prize. Okay, so now we're in a situation where it's combinations, right? Because order doesn't matter. They're just a winner. They get the same thing whether they're selected first or selected last. Sorry. And therefore, if G is the set of all possible groups of winners, then the cardinality of G is 11 choose 3, which is 11 factorial over 3 factorial times 8 factorial, which if you simplify that is 165. Okay, so when we're looking at a 20-member group that's selecting 3 officers. How many ways can that happen, assuming the same person cannot hold more than one office? And we're definitely back into permutation. So let's jump into our notebook. Okay. And what are we doing? Well, this is permutations, right? So what am I doing? I'm going to do, there are 20 members of the group, 20 sorority members, right? And they're choosing 3. Excellent. And you'll notice that 6,840 does in fact match what we calculated here, where some of those algebraic simplifications are shown for us along the way. How many digit numbers can be formed using 3 and 7 only? Okay, so what's going on here? We're actually in base 2, right? We're only allowed 2 numbers, the 3 and the 7. It doesn't matter whether you call them 0 and 1 like you would if we were in base 2, or if you call them 3 and 7, there's only 2 of them, right? And so the idea here is simply that there's 2 to the 10th binary numbers with 10 digits. Okay. And to remind you, we just use the caret symbol in our notebook and get the exact same thing. Okay, so here's the handshake problem. Um, okay, this is backwards, right? They've given us the total number of handshakes that occur, and they've asked us what the total number of people is in the room. Okay, so quickly talking about what's going on here, let's say there are 4 people in the room, right? The first person has 3 people to shake hands with, right? And then the second person has 2 people, and the third person has 1. So that was 3 plus 2 plus 1. So we are counting down from, and we're summing all the numbers between 1 and n minus 1, right? The group size is n, right? And then the sum of all the consecutive integers from 1 to that n minus 1 number is what we're doing. So let's jump over here and actually take a look at it, right? Why? Because we can use 1:4 to sum all the numbers between 1 and 4. So that adds up 1, 2, 3, and 4, and we get 10. Well, then this is fairly easy. We're like, okay, let's see, let's go to 6. If there's 6 people in the room, oh, there's 21 handshakes. And if there's 8 people in the room, oh, there's 36. And if there's 11 people in the room, I'm sorry, that would be 12 people in the room, right? The 11 is the n minus 1, which is the exact right thing to think about, right? So this is if n minus 1 equals 11, then we have 66, right? Therefore, right, n equals 12. There are 12 people in the room. The first person shakes 11 hands, and the second person shakes 10, and the third person shakes 9. And so we go 11 plus 10 plus 9 all the way down to plus 2 plus 1. And that's the correct answer. And here's a little diagram so we can see what's going on with n equals 2, n equals 3. If you think about the number of people, it's really easy for 2 people, 3 people, 4 people to count the number of handshakes. And as we do that, we can see the pattern growing. And again, that works for up to 200 or 300 people in the room, although I'm not sure if there are 300 people in a room, all of them are going to shake hands with every other person. But if they were to, we know how to calculate it. We just add up the consecutive positive integers between 1 and n minus 1. So here's another question. In college football training session, they line up the players in a row, and among these players, there's a freshman, a sophomore, there's a freshman, 2 sophomores, 4 juniors, 3 seniors, respectively. And how many different ways can they be arranged if only the class, their college level class, freshman, sophomore, junior, senior, is going to be distinguished. Okay, and so this confuses a lot of people, but what are we doing? We're basically asking, wait, how many distinct permutations of the 10 letters F, S, S, J, 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 R, R, R exist, right? If that's all, it doesn't matter what their name is or how tall they are. It doesn't matter anything except whether they're freshman, sophomore, junior, or senior. Okay, so we're just saying, hey, in how many different ways can we permute this? Okay, and the answer is, well, 10 factorial. Anytime I have 10 objects and I'm trying to permute them, I have 10 factorial. The problem is where it comes to distinct permutations, right? So where there are the sophomores standing, we could swap the order. Let's say that Joe and Sam are both sophomores. Joe could be first in line and Sam could be last, or Sam could be first in line and Joe would be last, and we couldn't tell the difference, right? That's why we're dividing the 10 factorial by 2 factorial. That's going to sort out the two S's. And then this 4 factorial, why? Well, there are 4 juniors. And again, we can't tell the difference among all the 4 factorial permutations of the juniors. And same with the 3 factorial permutations of all the seniors. So we take 10 factorial divided by the quantity, 2 factorial, 4 factorial, and 3 factorial, which is 12,600. Okay. Um, and so here we can do, remember, we're always able to do factorial, right? And then we can divide by these factorials, right? We divided by a 2 factorial times a 4 factorial times 3 factorial, 12,600, which does in fact match up to what we think it should. Okay, so we're doing well here. And notice that this will come up a lot. Okay, this idea of, let's say we have all the letters in the word Mississippi and how many unique arrangements exist, okay, or how many distinct permutations, unique arrangements, those are same words, synonyms, sorry. Okay, and that will come up. Same thing with, the letters in the word Alaska. How many unique arrangements are there? And again, it works like this with the number of letters factorial divided by the different groups of repeated letters, each to the factorial. So that's a good pattern to remember. That will come up a lot in the course. Sorry, there we go. So these home buyers have a choice of 4 different layouts or floor plans. They have 3 different heating systems. They can have a garage or a carport and a patio or screen porch. How many different plans are available to this buyer? Okay, well, let's just do that one over here. Right, so the first thing, they have 4 layout plans, right? Times 3 different heating systems. They get to choose a garage or a carport, and they get to choose the patio or the screened-in porch. There's 2 choices there. So 4 choices for the layouts, 3 choices for the heating system, 2 choices for the garage carport option, and 2 choices for the patio or screened-in porch. Right, so there are 48 different plans that are available to this home buyer. Okay. And in how many different ways can a true-false test consisting of 8 questions be answered? Well, there's 2 options. So again, we're in base 2, right? 0 or 1, true or false, right? So the correct number is 2 to the 8th, right? And we can answer that here. Same thing, you just write 2 caret 8, shift enter, and we have 256. All right. And how many different ways are there to select a subcommittee of 7 members from among a committee of 17? Again, order doesn't matter. I guess they're going to choose their chairperson after they meet in committee the first time. So the subcommittee, all seven, the order does not matter whether you're chosen first or last, you're still in this subcommittee, right? So it is going to be combinations, this choose notation, 17, choose 7. Okay. And if I do 17, choose 7, it's combin 17, comma 7, and there are 19,448 possible ways to choose this subcommittee. Now this one's fun. How many four-digit numbers are there where the digits appear in strictly increasing sequence? All right. So if all four digits have to be different, right? And why do they have to be? They have to be different because this is a strictly increasing sequence. We don't have 3, 3, 4, 4. Why? Because 3 isn't strictly bigger than 3. So I can't have two threes in a row. I can't have two fours in a row. So I can't have two of the same value in a row. So that means that all of them have to be different. So draw without replacement, right? But let's do this. We'll be careful. So 10, choose 4. Now, by the way, this is allowing us to have numbers, four-digit numbers like 0101. And a lot of us would think of this as 101, a three-digit number. But for the moment, right, to make the math simpler, we're saying, oh, 0 can be a leading digit. And that's typically not what we allow. But we'll talk about that at another time. Okay, now the question is, we have this many ways to choose four different digits to be in our four-digit number, but the question is, how many of the 4 factorial permutations of these digits will be in strictly increasing order? And the answer is just one, right? There is just one of those that's in strictly increasing order. So that's the correct answer, 10, choose 4. Okay. And now we get to how many different ways can the letters of the word leading be arranged in such a way that all the vowels are together? Okay. And let's talk about what we're doing because the vowels are the E, the A, and the I. But the main thing to do is to treat the vowels as a single unit. Why? Well, they're going to be together. They have to be together. Now, we can order them in a minute, but thinking of these three, how many others do we have? Well, we have consonants here, 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 and here. So we have 4 consonants and 3 vowels. So we have 5 items that are being permuted. That's the 5 factorial. But inside this group of 3 vowels, E, A, and I, there are 3 factorial ways for the different orderings of those 3 vowels. Okay? So, there are 5,040 total orderings, right? If we do 7 factorial, I think. Um, and then the ways that it can happen with those 3 vowels together, there are 720. Okay. So if you want to see that done, let me get rid of the marks on the screen there. If you want to see that done, right, we have factorial 5. Why? Those are the 5 units. If we treat the A, the E, and the I, the vowels, the group of vowels, all as one thing, there are 5 factorial ways. But then inside the group of 3 vowels, we have 3 factorial, and there we go. That's the 720. 10 people go to a party, and how many different ways can they be seated at a round table? Well, again, like we did with the handshake problem, think about this, right? Remembering that, um, let's say with 4 people, right? With 4 people, let's think of a clock face, they're seated at 12, at 3, at 6, and 9, right? But I can rotate that circle, that table, 90 degrees, and it's not a different ordering. They're still seated in the same order. They're just facing a slightly different direction. Same thing if I rotate another 90 degrees. So for 4 people, it's not 4 factorial, it's 3 factorial. So it's n minus 1 factorial. Okay, and so then 10 people go to a party. If they're going to be seated at a round table, right, we're going to do factorial 9y because n equals 10, right? And the solution is n minus 1 factorial, n minus 1 factorial. So we do 9 factorial, which is 362,880. Okay, so Jane and Thomas are among the 8 people from which a committee of 4 people is to be selected. How many different possible committees of 4 people can be selected from these 8 people if one of either Jane or Thomas is to be selected? Okay, so let me draw a little picture here quickly, right? So if we have these 8 people, right, and we draw a partition, there are 2 people here where Jane and Thomas are, and there are 6 people over here. So what happens is we draw from the left side of this partition a person, and we draw from the right side of the partition the other person. Okay, so what that looks like is, right, the way they can choose, um, we would have to calculate 3 things using these partitions, right? We'd have to contain the one where both Jane and Thomas were selected, and then Jane being selected by herself, or and add to that Thomas being selected by himself, but ruling out the times when they're selected together because they're already counted over here, right? So this is rather complicated, but here we go. Finding the complement is much easier. How many ways are there to select a committee, right, that do not the opposite of having Jane or Thomas in it? Okay, well, that's fairly easy because now we're selecting from, right? Now we're selecting from just the 6. Sorry, I meant the wrong one. We're just the 6, right? And we get down, sorry, to the 6, choose 4. All right. But that's the number of ways to exclude them. So we'll have to do a little subtraction to figure out the value of, we'll have to figure out how many ways we can do it, right? So let me get rid of the markings and we can do this, right? So what are we going to do? We're going to do, sorry, combination 6, choose 4, but and what's the total? The total number of things, what are we doing? From 8 people, we're selecting 4, right? So 70 ways to select the committee, 15 ways that neither Jane nor Thomas is among them, right? So I actually am doing combin 8, choose 4. That's the entire sample space minus the ones that don't include, that include neither Thomas nor Jane. So there are 55 ways to choose this committee in a way that does include either Jane or Thomas or both. Okay. A keypad has 10 different digits and a sequence of 5 different digits must be selected for the lock to open. How many keypad combinations are possible? Okay. There are 10 different digits, so you would think this would be 5 to the 10th, right? But that's if the digits can repeat. 5 to the 10th is if the digits can repeat. What we need to do is the permutation not the combination, the permutation. Why? We aren't just choosing uh, 5 different digits because the order matters, right? And a combination lock, being selected first is different than being selected third or fourth. Okay, so we're doing 10 permute 5. And there we go. Okay, so we're going to talk a little bit about partitions. I showed that a little bit 2 questions ago. Um, the idea is that we're counting the subsets in the partition rather than trying to count everything in the all the possible combinations, right? So, I mean, the idea of a partition is just like it is in a deck of cards, right? Where we have the hearts partition with 13 cards, and we have the spades partition with 13 cards, and we have the diamonds partition with 13 cards, and the clubs partition with 13 cards. And so, if we're playing a game of spades and we know that we need 7 spades, for example, we can calculate the probability of 7 spades. How? By doing 4 choose 1 to select one of the partitions, hopefully spades, right? And then we can do 13 choose 7, right? From the 13 cards in this part of the partition, we need to select 7 of them. So we'll go over this in more detail later, but just to give you a quick flavor, those partitions can be extremely valuable and assist us as we're trying to count things up. Okay, so here we have 5 women and 6 men in a group from this committee is to be chosen. How many ways can a committee be formed that contains 3 women and 1 man? Okay. So let's draw this partition out here. Right, so we have the men on one side of the partition and we have the women on the other side of the partition, right? And there are 5 of the women and there are 6 of the men. Okay, so what are we going to do? Well, 3 women, we're going to select 3 from the right side of the partition and we're going to select 1 from the left side. So on the left side of the partition, it's just 6 choose 1. And on the right side of the partition, it's going to be 5 choose 3. And I'm a bit confused. I just paused for a second because I seem to be using different numbers of men and women, 7 and 6 instead of 6 and 5, right? So I believe this is incorrect. The one that we had was 6 choose 3. Excuse me. Yes, 3 women and 1 man. So we're going to do 5 choose 3. Let me just get rid of this for a second, right? Um, So 3 women. So we're going to do combin 5 choose 3 times combin 6 choose 1. Why? Because there are 6 men. So 6 choose 1. There are 5 women. So 5 choose 3. And sorry about the mistake between the notebook and the PowerPoint. My apologies. Oh, I bet this is what, well, that may have happened. All right. So out of 7 consonants and 4 vowels, how many words of 3 consonants and 2 vowels can be formed? Okay, we're going to use combinations to draw the letters, right? We have 7 consonants, so 7 choose 3 to get 3 consonants. We have 4 vowels, so 4 choose 2 to get 2 vowels. But there's a question mark here. Why? Well, they're distinct, but there's lots of different orderings that can be added. So we have to think about this. This is the right number of letters, but this includes all the different ways they can be ordered into different words. They're all 5 factorial times this are unique arrangements, right? So um, I'm not sure what the 11 choose 5 is. Again, I'm sorry, there appear to be a couple of typos on these slides, and it is my bad. Just the numerator is the correct answer, and then just the numerator multiplied by 5 factorial is the correct answer. So I'm going to jump on to the next one and mention that when it comes to partitions, poker hands is one of the best illustrations of how to use partitions, and some of those calculations can be a bit tricky, so that's going to follow along soon. At the pizza place, there are 8 toppings you can put on your pizza. If you can order any number of the 8 toppings, then how many different toppings could you possibly order? Well, it depends on what we do with the cheese pizza. Is the cheese a topping? So that's a 1 topping pizza, or is it not a topping? Is it a 0 topping pizza? Okay, and if we count the cheese pizza as a 0 topping pizza, then there are 8 choose 1 topping pizzas, and 8 choose 2 topping pizzas. These are all the 3 topping pizzas, 4 topping pizzas, and we can order all 8 toppings. So we're adding these numbers up. And it turns out this is a little fact from the binomial theorem that these are all the binomial coefficients if I'm expanding a binomial like x plus y, quantity raised to the 8th power. Okay, so I know that these coefficients have to add up to be 2 to the 8th. Now, you can add them if you like. That's not a problem. But this just comes from some knowledge of the binomial theorem. Okay, find the number of ways to take 20 objects and arrange them in groups of 5 at a time where order does not matter. Well, I can start by choosing a group of 5 unordered objects from 20, but that leaves 15 to choose from. So then I choose a group of 5 from those 15, but then there's 10 left over, and I choose a group of 5 from them, and then 5 choose 5 is 1. So this is what it comes out to. Just like there's a binomial theorem, there's a multinomial theorem, and this relates to the way we do the multinomial coefficient, which isn't a part of this course, so we'll leave it alone for the moment, right? But to do this, right, we can do comben 20 choose 5 times comben 15 choose 5 times 10 choose 5. And again, this should be 5 choose 5 should just be 1, so it shouldn't matter. So I should get the same thing. Let's just see if we have our formula working properly. Same exact answer either way. Why? Because 5 choose 5 is equal to 1, as is 5 choose 0. So both 5 choose 5 and 5 choose 0 are equal to 1. Why? Because there's exactly one way to choose all 5 objects, and there's exactly one way to not choose all 5 objects. That second one confuses some students, but we'll talk about that as we go forward. Okay, so I believe I'm going to stop the video here. It's getting long, but we'll come back with a part 2 of the video, starting with the additional practice problems.